Right now, as you're watching this, one half of the Earth is sweltering in summer while the other half is buried in winter. Same planet, same sun, same moment in time. And here's the strange part. The reason has almost nothing to do with how close we are to the sun. In fact, Earth's closest to the sun in the first week of January, right in the middle of a northern winter. So if distance isn't the answer, what is? Why does the Earth have seasons? Let's start by killing the most popular wrong answer, because almost everyone believes it at some point. The idea goes like this. Earth's orbit isn't a perfect circle, it's an ellipse. So when we swing in close to the sun, we get summer. When we drift far away, we get winter. It's clean, it's intuitive, and it's wrong. Here's why. Earth's orbit is an ellipse, that part is true. At our closest point, called perihelion, we're about 147 million kilometers from the sun. At our farthest, aphelion, about 152 million. That gap sounds enormous until you realize it's only about 3% of the total distance. Real, measurable, but nowhere near enough to turn a beach into a snowfield. And then there's the fact that buries the theory completely. Perihelion happens in early January. Aphelion happens in early July. If distance drove the seasons, January would be the hottest month on Earth and July the coldest. Anyone living north of the equator can tell you that is not how it works. Worse, the theory can't explain the single most important fact about seasons. When it's summer in Argentina, it's winter in Norway. One planet, one distance, two opposite seasons at the same instant. Distance simply cannot do that. Something else has to. That something is a tilt. Earth doesn't spin upright. Its axis, the imaginary line running from the North Pole through the center to the South Pole, is tipped over by about 23.5 degrees relative to the plane of its orbit. And here's the crucial detail, the one everything else depends on. That axis keeps pointing in the same direction all year long. It doesn't swivel to follow the sun. Whatever month it is, the North Pole aims at essentially the same distant point in space, right now very close to the star Polaris. Think of it like carrying an umbrella in a circle around a lamp. You never rotate the umbrella, you just walk. On one side of the circle, the top of the umbrella leans toward the lamp. Half a lap later, on the opposite side, that exact same tilt now leans away. Nothing about the umbrella changed, only your position did. That's the whole mechanism. For half the year, the northern hemisphere leans toward the sun, and the southern hemisphere leans away. For the other half, they swap. Seasons aren't about distance, they're about angle. But why should leaning toward the sun make things warmer? It does two things at once, and they stack. The first is the angle the sunlight strikes the ground. Take a torch and shine it straight down onto a table. You get a small, bright, intense circle. Now tilt it so the beam arrives at a shallow angle, and the same light spreads out into a long, dim ellipse. The energy hasn't changed, it's just being smeared over more surface. Sunlight does exactly this. When your hemisphere leans toward the sun climbs higher in your sky at noon, and its rays hit the ground closer to head-on. Concentrated energy per square meter. When your hemisphere leans away, the sun stays low, the rays arrive at a slant, and that same energy is spread thin across more ground. Every square meter gets less. There's a bonus effect too. Light arriving at a shallow angle has to cut through far more atmosphere to reach you, more air to scatter and absorb it before it ever warms the surface. That's part of why a low winter sun feels so weak, even on a perfectly clear day. The second effect is time. Because of that same tilt, the hemisphere leaning toward the sun spends more of each rotation in daylight. Days stretch out. In London, in late June, the sun is up for about 16.5 hours. In late December, it's barely 8. So you're not just getting more intense sunlight, you're getting it for twice as long, while the night that's supposed to cool everything back down is cut in half. Heating wins by a wide margin, day after day, and the surplus accumulates. That's summer. Flip both of those. Weak, slanted light for a short day, followed by a long, cold night. Now the deficit accumulates instead. That's winter.
Now let's walk one lap around the sun and name the checkpoints. Around June 21st, the North Pole is tipped as far toward the sun as it ever gets. Northern days are at their longest, the noon sun at its highest. That's the June solstice. Summer begins in the north and winter begins in the south on the very same day. 6 months later, around December 21st, Earth sits on the opposite side of its orbit. Same tilt, same direction in space, but now the North Pole leans away. Northern days are at their shortest. That's the December solstice, winter in the north, summer in the south. Halfway between those two, around March 20th and September 22nd, Earth reaches the points where the tilt leans neither toward nor away from the sun. Sunlight falls most directly on the equator, and day and night are close to equal almost everywhere on the planet. Those are the equinoxes, the handover between seasons. And notice what the tropics actually are. The Tropic of Cancer and the Tropic of Capricorn at 23.5 degrees north and south aren't arbitrary lines on a map. They mark the furthest north and south the sun can ever be directly overhead. They are the tilt drawn onto the globe. Here's a puzzle that trips people up. If the June solstice delivers the most sunlight of the year in the north, why isn't June 21st the hottest day? Why are July and August usually worse? Because the Earth takes time to heat up. Soil, rock, they all have thermal inertia. As long as the ground is absorbing more energy each day than it radiates back out to space, temperatures keep climbing even after the daily sunlight has started to decline. The peak temperature doesn't arrive when incoming energy peaks. It arrives weeks later, when incoming and outgoing energy finally balance out. It's the same reason the hottest part of the day is mid-afternoon, not noon. Scale that lag up from a day to a year, and you get the seasonal lag, usually about a month to 6 weeks, and longer near big oceans because water is stubborn about changing temperature. Push toward the poles and the tilt stops being subtle and turns spectacular. Above the Arctic Circle at 66.5 degrees north, which is just 90 minus the tilt, there are days in summer when Earth's rotation never carries you into shadow at all. The sun circles the sky and refuses to set, the midnight sun. 6 months later, the same geometry runs in reverse. The sun never rises, and you get polar night. At the poles themselves, that becomes a single 6-month day, followed by a single 6-month night. Meanwhile, near the equator, the tilt barely matters. Day length stays close to 12 hours all year. The sun is always high, and the temperature hardly budges between January and July, which is why tropical regions don't really have summer and winter. They have wet and dry seasons instead, driven by shifting rain belts rather than by heat. So the seasons come from a 23.5-degree tilt, which raises the obvious question, why is the Earth tilted at all? The leading explanation goes back to the violent early solar system. About 4.5 billion years ago, a Mars-sized body, usually called Theia, is thought to have slammed into the young Earth. The collision blasted a huge amount of debris into orbit, and that debris eventually came together to form the Moon.
A glancing impact like that would also have knocked the Earth off vertical and left it spinning at an angle. In other words, our seasons may be the leftover echo of the worst day on our planet's history. And the moon that came out of it does something remarkable in return. Its gravity acts like a stabilizer, holding Earth's tilt inside a narrow range, drifting only between about 22.1 and 24.5 degrees over a 41,000-year cycle. Mars, with only 2 tiny moons, has no such anchor. Its tilt is thought to have swung wildly across its history, dragging its climate through extremes. Without our moon, the seasons you know would be a temporary arrangement. Even our narrow, stabilized wobble matters. Slow changes in the tilt, the shape of the orbit, and the direction the axis points combine into what are called Milankovitch cycles. They barely change the total energy Earth receives. They just change where and when it lands. And that alone is enough to nudge the world in and out of ice ages. And if you want to see how much a tilt defines a world, look outward. Venus is tilted almost not at all and has essentially no seasons. Mars, at about 25 degrees, has seasons a lot like ours, just twice as long. And then there's Uranus, tipped a staggering 98 degrees, essentially rolling around the sun on its side, where each pole gets 42 years of continuous daylight, followed by 42 years of darkness. So the next time someone tells you it's cold because the sun is far away, you can tell them the truth. In January, the sun is as close as it ever gets. What's really happening is that our planet is leaning, quietly, stubbornly, in the same direction it has leaned for billions of years, while it carries us around a circle. Sunlight arrives at a slant, the days run short, and heat drains away faster than it arrives. Winter isn't distance, it's geometry. And so is every spring that follows it. If this cleared something up for you, subscribe and tell me in the comments which planet you'd least want to spend a year on. My vote is Uranus.